Hello everybody, my name is Patrick Synor and I'm the manager of cloud architecture for a company called SolvIT. Today I'm going to discuss NGINX+ and highly available WebSockets in an auto-scaling AWS environment. Here's some background on SolvIT. SolvIT is a Michigan-based technology solutions provider. Our expertise includes cloud hosting, infrastructure and migration, application development, automotive technology, and managed help desk support. We're also an AWS partner and we have been since 2016. We have a wide range of customers in both domestic and international markets, including Fiat Chrysler automobiles. We were also named a top workplace in Michigan since 2012, and we're very proud of this. So here's what I hope to cover in this presentation. We're going to discuss cloud migration initiative and strategy. So why would you move to the cloud? And if so, we're going to share some tips on how you can be successful. We're going to discuss the need for WebSockets and the challenges they pose. We'll discuss the load balancing requirements in Amazon, as well as some challenges associated with load balancing in Amazon, particularly related to WebSocket load balancing. We'll discuss the introduction of NGINX and NGINX+ in our environment, as well as some benefits of NGINX+ over the NGINX Community Edition. We'll discuss an implementation from a project that we worked on in 2016, where we'll review the topology and some configuration examples. Finally, we'll review data from a production incident, in which case we lost a production NGINX load balancer. So why would you move to the cloud? Everybody's talking about the cloud these days, but is it right for you? The simple answer is maybe. It can be very appealing to have a dynamic infrastructure for a number of reasons. Traditionally, infrastructure components are static and have a relatively long life cycle. Infrastructure is typically a capital expense. In the cloud, however, infrastructure is typically an operational expense. A dynamic infrastructure can grow and shrink on demand, which can save money because you don't need to over-provision resources to account for variable traffic patterns. This model can also improve your resiliency by monitoring and replacing failed instances automatically. You can further reduce costs by allowing on-demand infrastructure for development and testing where you pay only for the components when they're active. On top of this, disaster recovery can also be significantly less expensive because you can minimize the operational cost by utilizing on-demand resources. In the cloud, scaling can also be much easier and more cost-effective. Resource availability in the cloud is generally not a concern. You can scale up, scale out, and scale globally with just a few clicks of a mouse. Traditionally, global scaling requires cost and effort to provision hardware and services remotely. All of this allows you to better align resource spending with your demand. In the cloud, operational overhead is also reduced. You no longer need to manage resources to support the physical components of your infrastructure. Operations staff can focus on their core competencies since they don't need to worry about scaling. And in some cases, they don't even need to worry about production issues because some issues can be self-healing. Management overhead can also be reduced as well. In the cloud, it's easy to account for resources and forecast costs. Traditionally, this is very challenging because components are often leveraged across physical infrastructure. Lifecycle management in the cloud is also a non-issue. The latest hardware is typically available to you in the cloud. You no longer need to worry about asset depreciation, obsolescence, and end of life. You can also potentially benefit from economies of scale. It can be tough to compete with the resource costs in the cloud. However, it's important to note that it's not always cheaper, so you must assess cost benefits on a case-by-case basis. Here are some tips for a successful migration to the cloud. Simply moving existing workloads to the cloud may fail because cloud infrastructure is very different than traditional infrastructure. Without re-engineering, you may run into failure when things become transient. Instances disappear, for example. Also, there may be limitations on functionality in the cloud that could affect your application or your application architecture. Re-engineer. Think about things such as stateful data. Identify components that require persistence. Try to anticipate managing an infrastructure without knowing where things will be and when. Forget what you know. In a traditional infrastructure, things are typically static. Due to this, you can often make assumptions about where things are and when, but that all goes out the window when you're in the cloud. Plan for things to disappear. You will learn very early on that things can and will move or disappear against your will. As we have, you may wake up to an email from AWS telling you that an instance may be unreachable due to maintenance, and further, the instance may be automatically terminated at a certain point of time. Because of this, you need to be prepared for what will happen when the resource is gone. Think about log data, session data, load distribution, monitoring, and availability. Practice chaos engineering if you can to ensure that your environment can survive a loss of any component at any time. Think cloud. This summarizes the above points. Train yourself to think of the nature of the cloud, not how things used to be. Leverage services. Hosted services can reduce your operational overhead and simplify some of the challenges associated with cloud infrastructure. Identify components that can move to hosted services and take advantage of them. This includes things such as hosted database services, hosted configuration management, hosted provisioning tools, as well as application container services, hosted cache, and many other. Finally, plan. Come up with a migration plan. Will you move one environment at a time, just DR, or will you maintain multiple environments concurrently while transitioning to the new environment? Try to determine this up front to minimize the risk. Additionally, try to identify variable versus constant workloads. Identify components requiring static resources. Identify access requirements, security requirements, geological requirements, and budget requirements. All of this will help you to better prepare for the eventual cutover to your new environment. For context, here are some technology milestones which led us to where we are today. In 2009, AWS launched the Elastic Load Balancer. 2 years later, the WebSocket protocol was standardized. In 2013, WebSocket proxying support was added to NGINX 1.3.13. Then in 2016, Amazon launched the Application Load Balancer. This all paints a very interesting picture. What we can see here is that the ELB launched prior to WebSocket standardization, so it's not surprising that there was no WebSocket support when the protocol was standardized. Within 2 years, however, NGINX supported proxying the protocol in NGINX 1.3.13. Unfortunately, WebSocket support was never added to the Elastic Load Balancer, which caused many complaints and feature requests because there was no native Amazon solution for load balancing of WebSockets until 2016. From 2011 to 2016, you were on your own if you were load balancing WebSockets in AWS. This is why many, including us, chose to implement NGINX. So why WebSockets? Well, let's be honest, it's not 1990. The web has evolved to an interactive platform with real-time interaction between clients and applications. Bandwidth has improved to support this model, which wasn't possible in the early days of the web. The old web consisted mostly of text and static content, so asynchronous HTTP worked. The request-response model worked well at that time since the nature of the web was mostly client browsers requesting information and servers gathering that information and returning it to the client. As the web evolved, however, problems arose with the development of applications that needed to send data to a client without a client requesting that information. Some examples of this are online games and real-time collaboration software. WebSockets solved this problem by allowing clients and servers to establish TCP socket connections via initial HTTP request, allowing bidirectional data flow as needed. This is also easy to implement today with stateful firewalls since there's no need to open additional ports on either side to support the communication. This all allows for more robust web applications. Unfortunately, some challenges came from this concept with load balancing web applications. The WebSockets open the door to new types of applications. It's not always easy to load balance them due to their unique requirements. These requirements don't always work well with different load balancing technologies. By nature, the WebSocket handshake should be routed to the backend node that handled the initial HTTP request. This means that some form of session persistence is required. This becomes a challenge with round-robin load balancing and can further be problematic with source IP-based load balancing due to split brain behavior in an active-active scenario. Another side effect of WebSockets is an increase in concurrent connections since connections aren't closed when a response is delivered. So here are some of the requirements we established for our application architecture. First off, we needed to support WebSockets. It was a requirement partly due to the nature of WebSockets, but also because our application communicated between the app server and the device in real time. We also required session persistence. There were other reasons aside from just the WebSocket load balancing that required that, so it was something we needed in our new architecture. The architecture also needed to be highly available. Our goal was to have an active-active multi-data center environment that could survive a complete data center failure. This ruled out any IP hash persistence models due to the split brain behavior that you would have in the event that a load balancer failed. We additionally required a level of fault tolerance. We needed to be able to detect unhealthy nodes and route traffic only to healthy ones. We also needed to preserve persistence when a load balancer failed, requiring a shared state of session distribution. We needed to account for dynamic infrastructure. Since the app layer is auto-scaling, we needed to be able to add and remove nodes to the load balancer continuously. Instances can come and go due to planned maintenance or unplanned downtime, and the load balancer needed to be able to detect these changes and change quickly. Finally, we needed proxy protocol support to preserve client IP addresses for logs and analytics. So here are some of the challenges associated with load balancing WebSockets with ELB directly. On the positive side, the ELB can be paired with auto-scaling groups, so nodes are managed automatically. The ELB also supports health checks. It does this with a simple HTTP health check or a TCP health check on a port. ELB is also, ELB is also naturally highly available. It supports multi-data center and it works in an active-active fashion. On the negative side, the only form of persistence for ELB is with an HTTP cookie. ELB operates in only two modes, HTTP and TCP. HTTP solves the persistence issue by inserting a cookie, but it does not understand the WebSocket handshake and thus breaks WebSocket connections. TCP mode simply routes connections, so it doesn't interfere with the WebSocket handshake. However, it does not allow for any form of persistence. It only works in round robin. Further, there are additionally some limitations on the health checks supported by the ELB. It can't do content checking, simply a status code. It sends a request, checks the status code for a 200, and that's it. Further, you have to use the same health check for all ELB listeners. This can be challenging if you're load balancing different applications with a single load balancer, since you can only specify one check for all of your backends. It's also important to note that the new application load balancer supports WebSockets natively. However, we're continuing to use NGINX due to the additional value added that we'll be covering shortly. For us, the solution to the ELB challenge was NGINX+. Because ELB cannot provide both persistence and WebSocket support, it was clear that we needed a new layer to handle these requirements. We evaluated other solutions, but found that the ones that we investigated could meet some but not all of our requirements. Further, some of them simply didn't work, and it was non-trivial as to why. When evaluating the community edition of NGINX, we did have some issues combining different community modules, such as the sticky module and active health check module. Essentially, the two modules that we used were not aware of each other. This resulted in NGINX delivering a client to an unhealthy backend based on a client cookie, despite the node failing the health check. Further, the lack of guaranteed support was also impeding the progress in meeting our customer timing objectives. Concluding our investigation, NGINX+ added a lot of value. NGINX+ natively supported WebSockets and sticky sessions. It also offered native active health checks where we could check the backends for more than just a status code. The built-in configuration API allowed for on-the-fly configuration of dynamic backend nodes, which allowed for service discovery in a dynamic environment. Lastly, the support agreements added a benefit in mitigating risk in a production environment. So here are some of the highlights of our comparison between the NGINX Community Edition and NGINX+. On the community side, cost is obviously the largest benefit. It's free to use. This is perfect for development and test environments and any environment that doesn't benefit from the added features of NGINX+. There's a large community for support, including blogs, IRC, Stack Overflow, forums, and many other sources. That level of support can be perfectly acceptable in testing and development. However, in production, this may not be sufficient. There's also a large amount of community-developed and contributed modules that add additional features to the native NGINX Community Edition. However, as we found, some of these can have compatibility issues. We encountered issues between modules that in our case were required. On the NGINX+ side, the biggest deterrent is obviously cost. It's not free, but there are different pricing models for different environment types and different support levels. For us, the cost was easily justifiable. The license support gave us guidance on configuration strategy and helped us work through some issues in our testing. This all helped us to meet timing objectives because we had an expectation on turnaround for support inquiries. Functionally, sticky and active health checks were native. Health checks were much more robust and allowed for content checking in addition to the simple HTTP checks. The configuration API allows us to leverage the Amazon API for service discovery. There was no longer any need to script modifications to the NGINX configuration directly and restart or reload NGINX. What this allows us to do is run with essentially an empty load balancing configuration and build the configuration dynamically based on what's currently in the AWS environment. So here's a high-level overview of the example application topology prior to migrating to AWS and NGINX+. The previous infrastructure resided in a single data center. This meant a loss of this facility involved an outage. In this environment, the load balancers were hardware-based and utilized round-robin load balancing with NGINX behind them. The load balancers were in an active-passive configuration, so any failure on the active unit would result in an interruption while the passive unit took over. In this case, we used the community edition of NGINX with the sticky module, but we didn't use the active health checks due to the compatibility issues. Further, this was acceptable in this case because the backends were not transient the way that they would be in an autoscale environment. Now, here's the new AWS topology. Here's a conceptual diagram of AWS hosting the exact same application. In this environment, traffic is distributed across data centers in multiple availability zones. The point of entry here is a classic ELB in multiple availability zones. They're configured with cross-zone load balancing, allowing them to talk to all of the NGINX instances. The ELBs are operating in TCP mode, so support WebSockets, and they're using round-robin load balancing to the NGINX servers. Here, NGINX is using sticky sessions to set a server ID cookie. We were able to confirm from our testing that the cookie value was consistent for the backends across different NGINX servers, so it doesn't result in a split brain when a user hits one server and then hits the other in round robin. This gave us consistent session states, so failure of an NGINX server would not result in users bouncing. Here, the NGINX servers proxy to multiple applications and can determine which servers are available for each pool. It does this using the AWS API and makes calls to it continuously. The NGINX servers make a call to their local configuration API to identify which servers are present, and then they add and remove servers based on the state of AWS. They also send HTTP health checks to the backend servers and require a quantity of success or failures to enable or disable a backend. This checks for the functionality of the backend as well as the version of the application that the backend is running. In this example, the database layer is leveraging Amazon's RDS, so we don't need to manage replication or placement of the database servers. Let's review a sample of the configuration for this scenario. This configuration is relatively straightforward. NGINX is proxying all traffic to one of the applications using WebSockets. The proxy param definition is simply used for configuring headers for the proxy protocol. This is done by enabling proxy protocol on the AWS CLI for the ELBs and also enabling it in the NGINX config. Then we're setting some headers to handle the WebSocket handshake. After that, we define criteria for the health check based on the response code and content returned from an HTTP request to a backend. We are requiring 6 successes to enable a server and 2 failures to disable a server. This is done every 10 seconds by hitting an internal resource on the backends. The health checks are used to monitor nodes that are currently in service, but also new nodes that still may be provisioning. This takes about 5 to 15 minutes in our environment, and the health check ensures that traffic does not hit servers which aren't ready yet. In this environment, all but the database are auto-scaling. This allows for the environment to self-heal, grow for demand, and rebalance if a data center fails. Here we have the configuration of the status page and the configuration API for NGINX+. On the left, we're defining a listener for our auto-discovery job. This is configured to only allow requests from the NGINX server itself. The listener is defined on an arbitrary port, 1234, and responds to configuration requests at /upstream-conf. On the right, we're defining a status listener on port 8080. This port is only open in the firewalls to private administrative networks for the operations staff. The server serves content packaged with NGINX+ that provides the status page resources. We're also defining a special status resource with a URI of /status. This resource provides JSON output including throughput, error counts, health checks, and other information. The JSON output is helpful for automation tools and integration with analytics tools. Next, we configure the HTML version to be accessed at /status.html. The HTML status page shows operations staff how NGINX is performing as well as the status of available backends. Finally, we're defining a stub status resource at /NGINX+Status. This is only accessible from the NGINX server itself as well. The stub status resource provides metrics on overall connection counts, connection states, and requests handled. Now let's talk about service discovery. Service discovery is rather trivial with an ELB and an autoscaling group. In that model, ELBs are directly paired with autoscale groups, and they automatically add and remove nodes as they come and go. This is sufficient for some environments, but we need a more complex service discovery for our use case. One reason for this is that only the NGINX servers in our environment are behind an ELB, so the ELB has no knowledge of the application servers that we wish to load balance. In our use case, NGINX is handling multiple applications in different autoscale groups with different configurations, so we needed to do the same sort of auto discovery that ELB was doing, but with NGINX discovering our application nodes. Surprisingly, the method used is nearly the same as what the ELB is doing. NGINX servers run these custom scripts continuously to query the AWS API and identify all of the IP addresses of nodes in a target autoscale group. The scripts then compare to the current NGINX configuration with a call to the local configuration API. After comparing, the script makes calls to the configuration API to reconcile the list of available servers with the list of the available servers in AWS. We also added a failsafe to the script. This failsafe detects failures in the AWS API and exits without making any changes to the local NGINX configuration. This is because we have seen issues with the AWS API, and it occasionally fails, and in that scenario, it would essentially wipe out all of the servers from the local NGINX configuration. Because we're using the configuration API of NGINX to manage the nodes, there's no service impact due to a restart or reload of NGINX whenever the backends change. Here's an example of the HTML version of the NGINX+Status Page. This is something that we use very often operationally. We use this page to assess overall health of the infrastructure. It provides a quick view of availability and performance. We can quickly see what's online, how many requests are being handled, response times, connection counts, throughput, and health check statistics. This page has also helped us to identify some servers that have failed to provision. Though it's rare, it does happen. In this situation, we typically know how long it takes for a server to provision. If this happens, we can see that a server is failing health checks for much longer than expected, and in that case, we try to log into the server to see what's happening. If we can't get in, we usually know something went wrong, and we simply terminate the instance and let autoscaling fix it. Another incident that this page has helped us to identify was an issue where a server was unhealthy but passing all analytic and operational checks. When this happened, we were able to identify the problem based on the connection count of a single server. This server had a connection count that was a small percentage of all the other servers. In this case, we were able to easily remove this server by just detaching it from the autoscale group, and a new replacement was launched and fixed the problem. Operationally, we also use this page to monitor progress of deployments. While servers are provisioning, we can see health checks failing here. Monitoring visually, we can tell when servers have finished provisioning and are ready for traffic. The health check used prevents us from sending users to unhealthy servers and ensure that they're getting the version of the code that we expect them to get. This page allows us to see this happen in real time. I'd also like to note that there's a lot of active development on the status page feature. We've seen a few features added since we started using it in 2016. One such example is the ability to manage backend servers from the dashboard, which can be enabled by turning on the write mode for the configuration API in NGINX. Now, let's see what happens when an NGINX instance fails in this scenario. This data was captured in Grafana for the application layer. The screenshot was captured during a production incident where an NGINX load balancer failed and was automatically replaced. The purpose of this data is to demonstrate what happens when we lose a production load balancer. In this case, a production load balancer failed the AWS internal health checks. These health checks monitor instances at the hardware and virtualization layer. When this happened, autoscaling detected the failure and launched a new instance to replace it. Here you'll notice a brief increase in connections on the app layer, which is a result of severed connections to the app servers and new connections being established through the available load balancer. Shortly after this, the orphan connections timed out and connection counts returned to normal. The most noteworthy metric here, however, is the app users graph. This graph shows that there was no impact to the user traffic during the incident, which is exactly what we designed it for. Now here are some key metrics from the NGINX layer during the exact same incident. On the CPU graph, we can see two servers running with nearly identical utilization. At the time of the failure, one server stopped plotting data and the other server had a spike followed by a marginal increase in utilization. On the ingress and egress traffic graphs, you can see traffic volumes increased on the healthy server. The connection counts also doubled on the healthy NGINX instance. Towards the right of the graph, you can see the point at which the replacement server came online and utilization and traffic began to rebalance. All of this happened with zero impact to user traffic and zero operational intervention. The architecture detected the fault and healed itself automatically. On a side note, you can see on the graph that there was a longer than normal turnaround for this replacement. Typically this takes about 15 minutes, but upon investigation, we found that resources in AWS were unavailable at the time. We were able to see this in the history of the Autoscale group in the AWS console. After a few failed attempts, the replacement launched successfully and began taking on traffic. With that in mind, make sure you anticipate this potential in your solutions. Although AWS is massive, there are still times when resources you need might not be available right away. So to summarize, the migration to the cloud presented many new challenges for us, but this forced us to architect such that we are now positioned better than we were before. We've seen a cost reduction by implementing autoscaling, which has minimized wasted resources due to over-provisioning for variable workloads. We've also seen a cost reduction in labor. We no longer need to manage resources to support physical components, so these resources have been reallocated to other projects where they're able to add more value. The self-healing and self-scaling infrastructure has freed up operations resources to focus on other projects and tasks. Though we've seen many benefits to migration, it's important to keep in mind that the cloud is not a silver bullet to improve performance and availability while reducing costs. In fact, costs in the cloud can sometimes be higher, so you should evaluate all projects on a case-by-case basis. You should perform a thorough analysis for each project to determine any cost benefits if cost is a motivating factor for you. Also, you may experience limitations in the cloud platform or your applications that could present a barrier to migration. From a technical perspective, the load balancing challenges that we had with WebSockets were more complex in the cloud than they were in traditional infrastructure. In traditional infrastructure, we could get away with IP-based persistence despite it not being an ideal method for load balancing. It worked, ensuring NGINX connection, or WebSocket connections and negotiations persisted to the right application servers. Moving to AWS, the ELB had limitations that forced us to change the way that we manage traffic. The most crucial limitation in this case was the lack of WebSocket support in HTTP mode and the lack of persistence in TCP mode. To solve this, we implemented NGINX+ with sticky sessions and active health checks behind the elastic load balancers. This architecture supports persistent HTTP and WebSocket connections which were required by our application. Though the new ALB would solve the WebSocket problem directly today, we're getting much more value from NGINX+ other than just WebSocket support. With NGINX+, we have the ability to do more robust health checking. We are also proxying specific resources to external services, defining different health checks for different backends, and much more. We have also been able to do some cool things by using simple tags on instances to modify the configuration of NGINX via the configuration API. With this information in mind, you'll need to decide what solution makes the most sense for your use case. I hope I've given you a little bit of knowledge and insight to help you succeed in migration to the cloud if it's something that you are considering. And I hope that this will help you to understand some of the potential solutions surrounding WebSocket load balancing if you go down that path. Thank you very much for your time. So any questions? Yes?
Did you guys evaluate service discovery?
Service discovery.
Like console, Zookeeper, anything like that?
No, that wasn't something that we looked into. We played around initially with the ELB. Once we found the configuration API for NGINX, we were already using it for many other things. It just made sense. It's simple enough. It's an API call to Amazon. We look for a specific tag, that's the autoscale group name, and then we make a call to the internal config and reconcile the two lists. So that it works for us. Anything else? Yes?
Can you tell us, in general terms, if you have to, anything about the WebSockets application that was created? Is demanding? Posed a challenge?
The particular application.
Real-time application?
Yes.
Demanding?
Yep. So the nature of the requirement for WebSockets in our particular use case is that there is a user session on one device, and then there is another part of that user session on another device. The two things need to pair up, essentially. So the user logs into the interface, and they're sitting there waiting for something to pop up on screen and say, oh, this is me. I want to start working with this device. We're doing that with WebSockets, where both ends are connecting to the server, so when the server sees the secondary device connected, it can push that down to the user session in the browser.
So that's also the need for persistence. Those two have to make it the same.
Exactly. Yep. Yeah, and WebSockets by nature kind of need persistence. Any other questions? Yes?
So are you using some part of NGINX to detect failure or need more resources to this one up, or is that just
We're using NGINX to detect failures at the application layer. So it's simply turning things on and turning them off if they're unhealthy. From a scaling perspective, we're using autoscale groups where we're defining CloudWatch alarms. So if the CPU hits a certain utilization for a certain period of time, add X amount of instances and then cool down, essentially. So we're actually managing even the NGINX layer and the application layers using autoscaling, but NGINX is solely just for service availability and health of the services.
have you explored to see if there is anything in NGINX that can detect that instead of relying on cloud?
Yeah, I mean, at the end of the day, we could use NGINX to do all of it. AWS is all API driven. So, I mean, could we have NGINX being the autoscale group and simply adding and removing servers? Absolutely. In our case, it just didn't really make sense to reinvent the wheel. What was there was already working. And NGINX kind of protects us from that scenario. We don't need to worry about the cooldown and the provisioning time that it takes for a server, where with autoscaling, you need to account for that and say, don't health check this thing for 300 seconds because I know it's still going to be building, or cool down, don't add the server right away. We don't care. When the box comes online, NGINX is the gatekeeper, and it can tell when that server is ready. So in the meantime, it just blocks all traffic to that server. It's something that we're considering. At this point, I don't know that we could benefit from it. It's very valuable when you have a workload that isn't time sensitive. In our case, it's a production environment, some development environments that are on-off depending on when they're being used. Because we don't do a whole lot of crunching where we need to just fire something up and get massive power, it really doesn't make a whole lot of sense for us today, but it's definitely something that we're exploring. No problem. Anything else? Yes?
You mentioned there was a case of false passes of the checks, the health checks, which say success, but the server wasn't processing the request.
Yep. So in that case, I personally never figured out why, and it was partly because the environment heals itself, so it wasn't worth our time. We looked into it. Very interestingly, we were seeing successful connections, successful requests coming through, getting the normal expected response. The health checks that we were doing were all passing. Unfortunately, the only thing that indicated any source of problem was the connection count was probably 10% of that of all the other servers in the pool. We couldn't figure out why, but when we simply pulled that one out and a new one was launched, everything was balanced. And we also, for grins, took that same instance, put it back in, and saw the exact same problem. So don't know why that one was failing, but that's the beauty of Amazon, is sometimes you don't need to know why. You build it to heal itself, build it so anything can go at any time, and it takes care of that for you. Anything else? Yes? I'm sorry? Is it stored outside of the NGINX box? I wish it was. It's something that I think we're going to be talking to the developers about, because it can be very problematic. You have multiple... Yep. Yeah. So they're not. What we found was essentially the method that it uses to generate the sticky cookie is consistent across different NGINX servers with different backends. So if you have the same backend server and 10 NGINX servers in front of it and it's using a hash-based sticky cookie, you'll get the exact same value for that same backend for all of them. So that allowed us to put the ELB in front using round robin, because it didn't matter if somebody hit one NGINX box or the other, they both had the exact same mapping. It's kind of coincidental. I don't know if that was intentional, but it's working for us. But what I would like to see is, as you mentioned, a shared session state table for the most part, something you could configure in like a Redis or a database where all of that session information of who's going where is behind the scenes and the NGINX boxes access it as needed. But that does not exist today. Anything else? No? Well, thank you guys very much.